All right, let's talk about differentiation. Specifically, that moment in calculus when the problems suddenly seem to get way more complex and you're left feeling like you're missing something. Well, I've got good news. You're not missing knowledge. You just need a better way to organize it. A toolbox, if you will.
So let's just jump right in. Over on the left, we've got the basics, right? A derivative you could probably do in your sleep. The derivative of 6x cubed? Push. Easy. 18x squared. But then you get this beast on the right. I mean, what do you even do with that? How on earth do you find a derivative when y is all mixed up in there? Well, that's exactly the gap we're going to close today.
And this, right here, is what I call the derivative dilemma. See, it's not about memorizing more and more rules. It's about building that toolbox. Think about it. You wouldn't use a hammer to saw a piece of wood, would you? Of course not. It's the same deal in calculus. The real secret is knowing which tool to pull out for which job. So you've got the power rule down. You know the product rule, the quotient rule, but you keep hitting a wall with these trickier functions. And yeah, it can be super frustrating. But the thing is, those basic rules, they're just the foundation. Now it's time to add the power tools to your collection. And the first, and honestly, the most important power tool we're going to talk about is the chain rule. Seriously, if there's one single technique that will unlock that next level of calculus for you, this is it. It's specifically designed for a very common type of function that can look really intimidating at first glance. That type of function is called a composite function. And all that means is it's a function living inside another function. You'll see it written as f of g of x. This whole function in a function idea is absolutely everywhere in calculus. And the best way to wrap your head around it is to think of a set of Russian nesting dolls. Yes, stick with me here. To get to that tiny little doll on the inside, you can't just smash it open, right? You have to open the outermost doll first, then the next one, and so on. The chain rule works in exactly the same way. You differentiate from the outside in, one layer at a time. Okay, so this whole Russian doll thing boils down to a super simple three-step process. Ready? Step 1, you differentiate the outer function. Just pretend that whole inner part is, I don't know, just a single variable, like u. The derivative of u to the fifth is 5 times u to the fourth, right? Simple. Now step 2, just copy that original inner function right back in, don't touch a thing. And finally, step 3, and this is crucial, you multiply the whole thing by the derivative of just that inner function. See? Outside, inside, multiply. That's the chain rule. It's a pattern. Now, knowing the rule is one thing, but actually applying it perfectly when you're under pressure, that's another story. As Professor Russell Blythe puts it, some problems are just magnets for mistakes. So let's look at a classic pitfall that trips up so many people, this time with the quotient rule. All right, pop quiz time. Take a quick look at this problem. Do you see the mistake? And hey, don't worry if it's not jumping out at you. It's a super common and really tempting error to make. Okay, you see it? Here's the error. The mistake was just taking the derivative of the top and then subtracting the derivative of the bottom. I mean, it kind of seems logical, but it completely ignores how the quotient rule formula actually works. This is one of those shortcuts that leads you straight to the wrong answer every single time. The correct way? You've got to apply the full formula, no shortcuts. Low d high minus high d low all over the square of what's below. Remember that? It's the derivative of the bottom times the top minus the top times the derivative of the bottom all over the bottom squared. Every single piece of that formula is there for a reason. The details really matter here. Okay, so you've got your power tool, the chain rule, and you know how to dodge some common mistakes. Now let's add a couple of highly specialized tools to our toolbox. These are for those really specific, really tough situations where the normal rules just aren't going to cut it. So first up, implicit differentiation. Let's think back to that beast problem from the very beginning. Remember, x cubed plus y cubed equals 6xy? Trying to get y all by itself on one side, that would be a total nightmare, maybe even impossible. So what do you do when you can't even isolate the variable you're supposed to be differentiating? The solution is this neat 4-step process. First, you just differentiate the whole equation term by term. The only new trick is this. Whenever you take the derivative of a y term, you just tack on a dy dx right next to it. After that, it's just algebra. As you can see in steps 2, 3, and 4, you're just getting all the dy dx terms on one side, factoring it out, and solving. It turns a messy calculus problem into a totally straightforward algebra problem. How cool is that? And now for our final tool. This one is designed for what feels like the ultimate challenge.
What in the world happens when you get a function like y equals x raised to the power of x? I mean, think about it. The power rule doesn't work because the exponent's a variable, and the exponential rule doesn't work because the base is a variable. We're totally stuck. Or are we? This is where logarithmic differentiation just swoops in and saves the day. Check out step 1. You just take the natural log of both sides. Why? Because it lets you use that amazing log property in step 2. You can bring that variable exponent right down to the front. And just like that, it's a multiplication problem, not a crazy exponent problem. From there, you just use the implicit differentiation we just learned to solve for dy dx. It is such an elegant hack for turning an impossible problem into something totally manageable. So, let's bring this all together. Real mastery in calculus isn't about being able to just recite formulas from memory. No, it's about looking at a problem, figuring out what makes it tricky, and then confidently reaching into your toolbox and grabbing the perfect tool for that specific job. And here it is, your cheat sheet. This is the big takeaway right here. Think of this as your decision-making guide. If you see a function inside of another function, your brain should immediately go chain rule. If you can't get y by itself, you know to go for implicit differentiation. You see a variable raised to a variable, that is a job for logarithmic differentiation. And a fraction, well, that's our good old friend, the quotient rule. See, it's not just a random list of rules anymore. It's a complete, organized system for crushing any derivative problem that comes your way. You have the tools, you know what they do, and now you know exactly when to use them. So the only question left is, with this brand new toolbox, what are you going to build?